All right, so done. Okay. Yeah, okay. So let's come back to the proof for this theorem 2.1.3. Right, so this is the setting. Okay, so so this is our what we want to prove. We want to prove that sine composite phi is a measurable function. Okay. So go back to the definition for measurable function. That will be like that. So from our setting here. So what is meant by measurable functions? So a measurable functions or measurable mapping. So it's a mapping which will pull back all the events to another event. Okay, so we need to put it back to another event. Okay. So that is the definitions for measurable function. Huh? Okay, now we want to show that this is a measurable function. So which means we need to verify that for all the events A in F3 that is in the range. So because if you come look at this picture, so this function sine composite phi is a function mapping from omega 1 to omega 3. So that's why we have to consider F3. Okay. So that's why this is what we want to prove. Given any event in F3, we want to show that sine composite phi inverse of this, the inverse image of A for these two, this mapping is on another event. So if we're able to prove this, then we can say that this function is a measurable function by using the definitions. Okay, so now what we need to do is we just need to make sure how to starting from here and get this stage. Okay, so maybe we're going backward. So let's look at this. So by using our the formula, so this will be given by sine inverse and then phi inverse sine inverse of A. Okay, so this is actually equivalent, same this. So in other words, we want to show that sine inverse of phi inverse A, it belongs to F1. So this is actually, you can look at this commutative diagram. So you can see, yeah. So if we go back, right, so that will be sine this to this, right? So that's why if you go back, so first we must have this one first. We must have a sine inverse first. Yeah, if you look at here, we should have a sine inverse and together with phi inverse. I put wrongly, right? Did I put wrongly? 1, 2, 2. Phi to here. Okay, we have this. Yes, right. I think then we have the other way around. So this one come first. Okay, so this one come first. Okay, so this is. Okay, in other words, we want to show that this is belongs to here. Then we just have to look at what is this one. So let me just look at this part. Okay, we just have to look at it. So then we can come up with our arguments here. Okay, since we know this, sine is measurable. Okay, so this is measurable. And from 2 to 3, right? Yeah, so this is in 3. So then we must have sine inverse A must be belongs to F2 because this is from 2 to 3. So 3 will pull back to 2. This is the one. Okay, now this one in here. Then we have a next since phi is measurable. Okay, so that's why this one acting on this must be belongs to F1. So because of this is from omega 1 to omega 2. Okay, so after 2 arguments, we have this. This is actually equals to this one. So then we can convince that this is a measurable function. So this is a standard ways applying the ideas of compositions of functions. Okay. Okay. Okay, here's the proof for it. Okay, so next remark 2.1.1. In fact, most of the mapping of that we encounter are measurable. So you can look at the theorem below. So next we will recall certain special real value function. Okay, so you can see all these kind of special functions are measurable. So that's why most of the mapping we can do are measurable. In fact, I'm putting most here. So in a way, actually, you can say all the standard functions are measurable functions. So you don't have to worry about it. Okay, so let's look at first one. Continuous function, I think something that you should have seen in calculus. The definition for continuous function is it will pull all the open set back to an open set. So that is slightly different from the measurable functions. Okay. So let's say if you have a function, so talk about it. So u to r. Okay. So we said that this function is continuous if and only if all the open set, so A subset to A in here is open. So you pull back, the pre-image will be an open in U. So when you change this to event, so that will be measurable function. So next one, I think is clear. We have seen this before, increasing function. So that means going up. So this is a decreasing function. So that's the mathematical criterion for it. So graphically, it will be like this. So if you have a graph like this way, so let's say, so going up, so this is an increasing function. Okay. Likewise, you can have a decreasing function, so that will be like this. So always this going down. Okay, so that means the red color will be decreasing. Oh, sorry, the green color function. So this is another. We just include this increasing, decreasing means a monotone function. I think that is one. Okay. Okay, so this is just a basic concept for it. Okay, next you can see continuous function are measurable, monotone function are measurable. So that means these 3 types of function are measurable. Okay, so I'm not going to prove this, so you just accept it. So at least from here you can see most of the mappings are measurable. Okay, including continuous, increasing, and monotone. So even if we have function like this, which is not continuous, right? You look at these 2 examples, not continuous. However, the green color one is decreasing, but the blue color one is increasing. So these 2 functions also measurable. Okay. Okay, now we come to the definition of random variable. So before that, so just go back to the measurable function again. So measurable function is a function from omega to omega 2. So this omega 2 could be any kind of the sample space. Okay, so in particular, when omega 2 is R, then it is random variable. Okay. So you can see the ideal. So recall back. So in this definition, you may just refer when omega 2 is equals to R. Okay, when omega 2 is equals to R, then this phi will be so-called is a random variable. Just like that. So actually it's exactly the same as this. What you need to do is you just need to replace omega 2 with R. Okay? So in other words, if you're using this, then you can have this remark, note. So a random variable is a real number value measurable function. Okay. So that means now random variable is a special kind of measurable functions. Okay. So a random variable is a special kind of measurable function. That is when omega equals to 2 in this definitely 2.1.2. Or 2.1.2, yes. Okay, 2.1.2. So when this is R, that means this is a random variable, just like that. So therefore, from here, then we can see because of continuous function, increasing function, decreasing function are all measurable, then we can see that all these functions are also random variables. Okay. So this is what I mentioned just now, meaning that random variables are measurable and real value functions. So two criterion here. Okay, next. If you want to verify whether a function is a random variable, so we have to do this verification. Just notes. Huh? Okay, maybe we follow the symbol X. Okay, if you want to verify whether a given function from omega to R is a random variable, yeah, of course, when we talk about this, we always consider, let's say it could be 1 sigma field F over here, and for R, we always consider the Borel sigma field B. Okay, so in order to verify this, so what we need to do is we need to ensure that this will be true. So whenever B is a Borel subset, then if you pull back X inverse B is an event in this omega. So this one we need to answer for all. So we need to verify for all B in for all Borel subset B, which have to fulfill this criterion. Okay. So however, we can actually have a slightly simple criterion to do it. Okay, in fact, we can replace this. Oh, okay, we can go. Okay, yeah, I think we can set. Can replace this with another easier method. Way. Okay. So in what sense? In the sense that by considering fewer subset B. So here we need to, if we want to use the definition, we have to consider all, we have to verify for all the Borel subset. So however, we can have a slightly easier way, that is we look at not all of them, just a particular kind of the Borel subset. So by verifying these smaller classes of subset, so it's enough for us to justify whether this is a random variables or not. Okay? So this is what we want to do now. We're looking for another way, another easy way. Okay? So let's begin with this notation. So this is what our definition here. Okay, so this is our convention because we don't want to write so many things here. Okay, we use a relatively easy, simple form. However, it's a bit confusing to describe some phenomenon. Yeah. So for example, we just simply write it x less or equals to b to be the inverse image for this interval, negative infinity to b. So it less or equal to b. So and x less than b will be the inverse image for this interval, negative infinity to b under this x. Similarly, we have if x greater or equal to b and less greater or equal to a and less equal to b will be this, and so on. Okay, so we use this curve symbol. So don't make sure you understand this curve symbol. So what's the meaning for it? So this is actually the pre-image for the interval ab under this function x. Okay. So we're going to use this kind of symbol throughout the whole course. In fact, this is kind of a standard notation. So it's widely used in most of the textbook in the topic of probability theory. Okay. So yeah, remember all this. Okay, next we look at these theorems. Okay, this theorem is very useful. So I put it here. So let's come back to here. So according to the, I mean this one, if we want to verify this using definitions, okay? If we want to use definition, so we have to ensure this is true for all B. Okay, now we can use a relatively easy way, that is using theorem 2.2.2. So this is a much better way. So we can use this criterion to judge. So if we have a function x okay, it's a function from omega to r. Again, we always assume this omega equal with 1 sigma field f. And again, when we take r, we always assume it's Borel sigma field b. Okay, so let's say x is a function from some sample space to r. So we say that this x is a random variable if and only if this criterion are fulfilled. X less or equals to b is an even. True for all real number b. So you can see we don't have to consider other parallel set. Okay, so here it said you have to consider all parallel set to verify it. So however, when we come to here, we don't have to consider all parallel set. We just need to consider a particular type of parallel set, that is this, the inverse image for this interval. So this one, if we use a symbol, so this is just equals to the inverse image for this closed interval, negative infinity to b. Okay. In fact, we can replace 2.1 with one of these criteria. So here saying that s less or equal to b for all b, we can replace with x less than b for all b in R. Alternatively, we can say a greater to x greater or equal to a for all a, or x greater strictly larger than a for all a. So actually, you may replace 2.1 with any one of these, no problem. So that's why you are not necessarily follow this. You can take one of this if you want to do some proving things. Yeah. Okay. So just to let you know, not just briefly verify this, why all these are equivalent. So let's briefly verify this. So this remark says that, so this is here remark 2.2.1 says that all these are equivalent. So let's say, what should I label? Okay, maybe I will follow 2.1. Okay, 2.1 said that x less or equals to b belongs to f for all b. And this one, maybe I just put, okay, maybe I just put R2. Okay, so R2 is x greater to a belongs to here for all a. Now, of course, all these are real numbers. And I put this as R3. A, x strictly larger than a. So for all a. Or the last one. So all these four are equivalent. So that means when R2 correct, so R3 must be correct. R3 must be correct. R3 correct, R4 must be correct. R4 correct, then 2.1 must be correct. Okay, so I just verify some of them for you. Then the rest you can check it out on yourself. Okay, so checking. Just part of it. Okay, let's say we look at it. 2.1, so this is easy. 2.1 to R4, this is easy. Okay, we verify this. Okay, we assume 2.1 true. Okay, we assume 2.1 is true. You may replace this with A. So let's say we can put this one to be A. So because of this is all number, right? So we can change to A. Okay, so then we can see for any A. So we want to verify this, right? Then we can see this. You can look at here. X greater than A must be equals to the complement of X less or equals to A. I think makes sense, right? Right, so the pre-image of X greater than this one, okay, X greater than A must be equals to the complement of X less or equals to A, right? Okay, so if we, according to theorem 2.2, this 2.1, so X less or equals to A, this set, the set X less or equals to A is an event. Yeah, so then we can see since it's an event. Okay, then we use back here for any event A, not this one. Okay, this one, A is an event, its complement must be an event. So this is A, capital A is an event, so the complement must be an event. Okay, that's the way from 2.1 to R4R. In fact, you can do it same, the other way around. So you can check this. If this one true, then this one must be true. Similarly, I think I put it wrongly. Am I right? X less. Oh, sorry. I think this one is wrong. It's supposed to be X less than B. Okay, X less than B. Okay, now I give you another one, so you can check out. So if R2 correct, then 2.1 must be correct. Okay. So next one. Okay, then this one you may do it on yourself. So let's say R4 correct, then check it on yourself. So you can check, let's say R2 correct, then 2.1 must be correct. Okay, why is that so? Okay, so we assume R2 is true. So we want to show that 2.1 is true. Okay, then okay, maybe this. We take B to be an real number. So then we must have this. So I think makes sense, right? What we can do is we may assume this is a new B to be this. Okay, we consider the same equation. So we consider a new B to be B minus 1 over K. Okay, so that means because of this is true for all B, right? So we're taking this B to be B minus 1 over K. So that's why this must the set of X less than B minus 1 over K must be an event according to this criterion 2.1. So this is one. Okay, next we can verify this. So X less than B must be equals to the countable unions of this. Am I right? Okay, so I think it's not 0. If I take union, so cannot. Okay, so maybe I put it this way. I put plus here. So I put plus here. Then instead of union, I would take intersections. Okay, I will take intersections. So you guys may verify easily on yourself. Just take a picture. You can imagine this picture. So let's say, first of all, this is from negative infinity up to B, right? Maybe you can just draw a long one. Okay, first you begin with B plus 1. So this is 1 over 1, so which is somewhere here. So let's say this is your B. B is always included, am I right? So I think maybe this is up to here. Yeah, so this is B. B is always included. Okay, so when you take data 1, so that will be from negative infinity up to here. So this is B plus half. Yet, which is still inside, you take another one, negative infinity up to here. B plus 1 over 3. So using this approach, you can see so 0 to B must be always belongs to all of them. So when you take intersection, so that means it always included but no other. Okay, using this way, so this one must be equals to this. So once we have this, we go back to our theorems. Okay, so here, this theorem said that if an event, so the intersection of this sequence of event must be even. So all these events, so this is the intersection of them. So this must be an event of it. Okay. So again, this is by theorem 1.4.1 part 2. Okay, so similarly, you can verify the others there. So easily using this kind of approach. So you can see this 2.1, I label this as R2, this is R3 and R4. These 4 conditions are equivalent. Okay, so in future, you may take any one of these conditions to verify whether a given function x is a random variable or not. Okay. So it depends on the pattern of the function. Okay, because in sometimes it will be more convenient if you take this criterion. It depends on the function x. Okay. So you can see here we have a rather easy way to check whether a given function is a random variable. So you can see here we just look at what do you call it? One particular type of interval. Sorry. Otherwise, we have to look at all kinds of the intervals. So this is one method, the general method for us to verify whether a given function is random variables or not. Okay. Okay. Next, we look at 2 different cases. Okay. So we have, as usual, when we have a random variable, we have 2 different kind of random variable. So one is the discrete. Okay. And the other one, the continuous one. What happened? Okay. In fact, we have other, but we leave it. We just look at it. So of course, we do have others. Okay. But forget about it. We basically look at things like that. Yeah. Okay. So we look at the first one. So discrete one, we have an easy criterion for us to test whether this is a random variable or not. So that is, we can replace by this. So in general, we have to look at an interval x less or equal to b, or x less than, strictly less than b for all b, or we look at x less or equal to b for all b. So for the discrete case, we can look at relatively simple criterion. Okay, what we need to do, we can just look at each of the point here. Okay. So that is, x is a random variable if and only if x equals to k belongs to here. For each image k in this. Right. Okay, let's look at our examples. So Okay, so for these examples, right, part A is the standard one. Part B is just a toy example to demonstrate the idea for you guys. Huh? Okay, so let's look at here. So example 2.2.4. So this is one example of discrete random variable. Okay, so here the setting, n unbiased cos is twice. So then we have omega is HH, HT, TH, and TT. Okay, so we define our function to be like that. So for each omega, we define x omega to be the number of head. So which means we associate each outcome here a number. Okay. X associated each outcome with a number. Okay. So have to be, this is a first criterion for something to be a random variable. Outcome, assign each outcome to a number. So I think using this, we can easily get this right. There are only 4 outcomes in this experiment. So therefore, we can have our omega. So let's say our HH. So the value for our x, we can easily, what is it? The number of head, right? So that's why this is 2. The next one, HT, this is 1. TH, this is 1. TT, no head, we got 0. Okay, so this table describe the value of x over here. Okay, so if we look at here, then it's quite straightforward. We can see x equals to 2 will be, there's only one possible outcome. So H, right? So x equals to 1. Okay, so there are 2 possible outcomes here, HT and TH. And lastly, x equals to 0. So that will be TT, yeah, in this case. Okay, so first we look at standard examples. Yeah, the standard case. Okay, so this is the standard formulation. Okay, so this is a standard formulation. So if we take F to be P omega. So if we take this to be P omega, you can see clearly all this must be subset to this F, right? So there you can see all this x equals to 2, x equals to 1, and x equals to 0 must be elements of F. So all these are even. Then we can see, hence, x is a random variable. Okay, so before we proceed to the second example, so just give you this remark. So I believe you no problem for you guys, right? The criterion for something to be a random variable is the pre-image of the event must be an event. Okay, so if we take F to be P omega, so that means all subset of omega are event. So that means the pre-image for any value here, any subset in R must be a subset in omega. So in this case, when f is p omega, the power set, then any function must be a random variable. So actually, we don't have to verify. When we look at this p omega, so any function, surely it must be a random variable. Okay, so this is just a remark for you. Okay, however, this is just to demonstrate the idea. Okay, how to verify something is random variables or not. Okay, okay. Next, look at another example. Okay, so this is a toy example. Let's say B. Okay, instead of p omega, okay, although we are still we are doing the finite case, right? Okay, although we are doing the finite case, so this is a toy formulations. So we're hearing toys mean this is just for teaching purpose. Okay, a teaching example to demonstrate the idea how to solve the problem. Okay, so let's say if we consider this f to be standard formulation, we're going to take PR. However, this one we just simply take our sigma field to be this. As well as the omega. Okay. Okay, come back to it. So you can see, actually it's here. I don't write down. So I think it's clear, right? You look at here. Yeah. X equal to HH, yeah, is here. Yeah, no problem. Okay, next we can either look at this or this. So you look at this one, for example. HTTH, so which is does not belongs to here. Same as this TT does not belongs to here, right? So therefore, I think I do want to write down. So we consider this. So x minus 1 does not belong to here. Then x is not a random. In fact, we can also use another reason. X inverse does not belong to here. Okay, so we can easily verify this. So this one, then we can see. So because of x equals to 0, which is not an element of f. So in this case, x is not a random variable. Right. So look from here, you can see actually whether a given function is a random variable or not. It actually depends on the choice of sigma field. Okay, next another example. So this is again another discrete example. This is what we so-called an indicator functions. Okay. So indicator function. Before we look at it, so just to recall, what is this so-called indicator functions? So remember it? No, sir. Just recall. Okay. So the definition for this indicator function will be 1 of omega, 1a omega will be equals to 1 when omega belongs to a. So 0 when omega is not belongs to a, belong to 1c. Okay. So if you give an example, so let's say if we take a to be this, let's say the closed interval 0 to 10. Okay, and we consider omega is R. Just examples. Yeah. So if we consider this, then 1a of 11 is equals to 0 because 11 does not belong to here. Okay, and next 1a of 5 is equals to 1, and so on. So this is what we so-called the indicator functions. I think it's clear. So 11 does not belongs to A, so we got 0. 5 belongs to A, so this is A. Right, so I think it's quite straightforward. Look at these examples. Okay, 1A is an indicator function of A. So then it has only two images, 0 and 1. I think it's clear because it's either 0. So then you can just look at it. So by here, then you can see the pre-image for 0 is AC. The pre-image for this indicator function 1 is equal to A. So you can see if we're taking A is an event, so yeah, A must be N. So the complement must be event. So it's fulfilled. This, okay, X in inverse K belongs to F for all the possible image. Here we only have two images. Okay, so this is here. Okay, we look at a more general case over here. So this is so-called a simple random variables. Okay, roughly speaking, not roughly, actually it's a precise meaning. So simple random variable is a random variable which takes only finitely many values. Okay, so as long as the images is a finite set, so it is a simple random variable. Okay. So then from here you can see indicator functions only two value, right? So it takes 0 and 1. So that means in this case, then we can see. So that's the indicator functions is a special kind of simple random variable. Okay, in general, you can see a simple random variable can always be written in this form. X is equal to summation of AK times 1AK. So here we always assume this is a partition of omega. Okay. First, we choose a partition A1, A2 up to AN. So which form a partition for omega, then we can just say X to be the summing of this, the linear combination of all these things. Okay, so then you can see number 3, the general form. So when A1, A2, okay, because this is finite, so we are not up to infinity, we only up to AM. So finite, so that's why we stop somewhere here. Partition. Events. Maybe I should say this one. Events and form a partition for omega. So So what's the meaning? Just to remind you again, what's the meaning for it? So this one, form a partition means first, all this must be disjoint. Okay, AM must be disjoint. Okay. First of all, there must be disjoint. Secondly, if you're taking the union of all of them, you're combining them. So this is omega. Okay. So when A1, A2 up to AN are events, so then we can define a simple random variable will be given in this form. So then we get X to be A1 So this one is a simple random variable. So you can see, if you look at here, it takes only m value, A1, A2 up to AN. So I think because you can easily verify here based on this, if we are taking all this to be event, okay, then we can easily show this. The value x equals to AI must be equals to AI, capital AI. So this is always belongs to F. Okay, so that's why we can see this is an event and this is so-called a simple event. So why I'm saying that indicator function is a special kind of simple event. So the reason is this indicator function, we can put it in this way. We can write our one, I think not a good choice. Okay, we can always put the indicator function 1a to be 1. I think not to use 1, I better use I here. Can always be written as 1 multiplying IA plus 0 multiplying the indicator function A complement. Okay, so that means we only have two A1 and A2 here. This is A1, this is A2 for it. Okay, forget it. So you guys can think of it. So up to here, we have discussed several examples. So example 2.2.4, 2.2.5, and 2.2.6 are all these are discrete, are in fact finite random variable. All are simple random variable. So you can see this one finite because we only takes how many values? So it only takes 2, 1, 0. Okay, finite. So this one 0 and 1 also finite. And this one is also finite up to m. Okay. Okay, next we look at another one. So this is a non-discrete one. So we need to spend a little bit of time how to derive this. Okay, so examples. Two point 2.7. Okay, we consider omega is 0 to 1. So 0, excluding 0, including 1. And of course, we consider our sigma field to be the Borel sigma field corresponding to this subset. Okay. Okay, now we are looking at x omega to be 2 omega plus 1. Okay, then we have this. So want to verify whether x is a random variable. So in fact, here, that's the answer. X must be a random variable. Okay, so there are two methods here. First method is easiest. Yeah. We refer back to here. This one. Okay, maybe we take this. Okay, first method is straightforward. Okay, here say that continuous functions are measurable. Okay, and random variable are measurable and real value function. So which means continuous function must be measurable. Continuous function must be random variable. So first method, we can actually make use of this theorem. Okay, so method 1. So it's quite clear. I think clearly x is continuous. Okay, I think clearly this is a continuous function. So x is a random variable. Okay, so this is directly by theorems 2.1.5. Okay, so we don't even have to do this. Okay, however, again, method 2, just to demonstrate the idea how to apply our theorems, how to apply our next theorems. This one, theorem 2.2.2, okay, just to demonstrate the idea how to apply this theorem. Okay? So then we look at method 2. So we do it using which one? I think theorems 2.2.2. Okay, in fact, I will consider remark 2.2.1 to be the same theorems here. Okay, so what we need to do is we need to show it what we want to prove. So what we want to do, we want to show for any B in R. Okay, for any real number B, so x less or equals to B must be belongs to our F. Okay, so which is actually the Borel set of omega. Okay, this is what we want to prove. Okay, so we just need to identify what is this set. So that's fine. Let's do our thing. So let B be any real numbers here. So we just need to look at it, how the set looks like. So we can verify this. So x omega is given just now. We can say x omega is, okay, this one 2 omega plus 1. So that's why we can say this is equals to 2 omega plus 1 less or equals to B. Okay, so this one we can express this as with some simple arithmetic. So we can see this is equals to omega less or equals to B minus 1 over 2. And come back to here, just remember our omega, our sample space is the interval 0 to 1. So that's why we have to restrict our small omega over here. Then we look at several cases. So B is in R. Okay, so that means if we look at our real line, so then we can look at here 1 and 3. So we can look at 3 different portions. So that is, first portion will be here. How should I say? Maybe, okay. Okay, we can look at 3 portions here. First, from negative infinity up to 1. Okay, and next, we look at another portions from 1 and then up to 3. And finally, the last portion will be from 3 onward up to infinity. Okay, so that's the range that we're going to consider. So this is a negative infinity, 1, 3, and infinity. So we look at 3 different portions for B. Okay, why we do that? Because of later on you shall see. Okay, one by one. Okay, so look at the case number 1. When our B is less or equals to 1. Yeah, so to be easy, you may just imagine. You can always imagine B is equals to 0. Just imagine this. You can work out the calculation on yourself. Imagine B is equal to 0. Okay. So in this case, if B is less than 1, so you can see B minus 1 over 2 will be less or equals to omega. Okay, less or equals to omega. So from here, less or equals to less or equals to 0. So we look at here, then we can see x less or equals to b must be equals to omega less or equals to 0. Okay, and remember, if we want to come back to this, this is how we define our. Okay, so how we define it. Okay, so if we consider omega is a subset of R, so the Borel sigma field on omega will be B intersect omega, where B is a Borel set. Okay, so that means when we look at here, we cannot just take B alone. Okay, this is our B. Okay. So this is our B. Okay. So then we cannot take B alone. We have to intersect with our omega. So that's why. So we have to intersect with our omega. So, but in this example, what is our omega? Omega is 0 to 1. So that means the small omega must be greater than 0 and less or equals to 1. So this is actually our omega. Can be the omega, and this is the B. So this is less or equal to 0. This is greater than 0. I think it's clear, right? So this is how we get then the outcome will be nothing because of no overlapping here. So this is why we get an empty set over here. So you can imagine B equals to 0. Okay, if B equals 0, so this is a minus half. Then definitely there's no intersection here. Right? So we likewise we can do for the other case. So for case 2, we can do similarly. When B is a number in between 1, 2, 3. So you can work out a calculation similarly. Then you can see this is always in between 0 to 1. Okay, when this is 0 to 1, then you can see your omega x less or equals to this. Okay, we can do the same thing. So that will be equals to this x, not this, omega less or equals to the same number, this intersect with, okay, maybe you can put it this way. Okay, same, like, okay, so when b minus 1 or 2 is between 0 to 1, so that is here, so that means this one must be the subset of this. Okay, so that's why we will get the same answer. This is not. Okay, so inside here, so we gotta put it here. So because we set a bound here, omega in between here. So if we express in the interval, will be 0, excluding 0, up to b minus 1 here. So for the last part, we can do the similar calculations. So this one you can do and imagine. Okay, you just imagine, or you can put a specific imagine b is 2. Then you can see the idea. Okay, so this one, finally, the last portion will be b greater than 3. Again, you can just imagine a number, a very big number. Just imagine b is 11. Okay, so you can see when this is greater than this, then you can have a similar calculations. b minus 1 over 3 must be greater than 1. So then you can see this must be empty set. Not empty set, actually the whole of them. So I think I better put it properly. Okay, when this is greater than 1, so this must be equals to omega between 0 to 1. Okay, because of this is larger than it. So this is how we get all these calculations. Okay, of course, you can actually use the easiest way to do it, just applying the theorem 2.1.5. And this is a continuous function. We can directly apply theorem 2.1.5 to do it. Yeah. However, this method too, just to demonstrate the idea to you guys, how to use this theorem 2.2.2 to solve the problem there.
Sorry, doctor.
Yeah.
I want to check with you. For number 3, right? Is it 1 less than b minus 1 divided by 2 or 3?
Thank you. 2. Yeah, thank you. Yeah, it's supposed to be 2.
Thank you.
Okay, so I think you guys get the ideas, right, for this one. Okay, maybe the last one, you get it, right? So just let's say this is b. Let's say this is your b, and this is your omega, right? And b minus 1 over 2 is larger than 1. So this is actually then you get this this set. Okay, you get from negative infinity and towards here. Okay, so this is your b minus 1 over 2. Okay, so this is because this is larger than 2. Okay, next, this is larger than 1. Okay, so it's here. So omega is from 0 to 1. So this is larger than 1, right? So that means 1 must be somewhere here. I don't know what could be here. Let's say 1 is here. If 1 is here, then 0 must be here, right? Because I'm taking this will be example. So if you take the intersections of these two, yeah, you take the intersection, then will be this, right? This is how we get it. So after taking the intersection, must be left. We only have the blue color things. So what you can do is, for example, you imagine a very large number for your B, then you can see the idea for it. Okay. Right. So this is the criterion for us to test whether something is a random variables or not. Okay. Next, we can actually use a lot of method to generate new random variable if we have some non-random variable. Okay. So actually, random variable is something that is quite common. We can easily generate random variable, and most of the functions are random variable. Okay. For example, okay, this one. If x and y are random variable, so the sum of them is random variable. You multiply by any constant random variable. Okay. So the maximum value for x and y and the minimum value for x and y are also random variable. The product of them random variable. The quotient of them random variable. So from here you can see there are plenty of ways for us to generate different kind of random variable. Okay. Okay. The proof is I can forget about proof, but the idea is like that. What you can do is you can make use of theorem 2.1.5. Yeah, that is this one. Alternately, you can also use this theorem 2.2.2 to verify it. So one way would be this. Where is our this? Okay, continuous functions are measurable. Okay, and so so you can use this to verify it. And you can see when x, y are random variables, so this is composition function are continuous. Okay, so we can say this. We define f of xy to be ax plus by. I think maybe I could. So f is continuous because this is linear functions. Okay, so this is measurable, and our ax plus by will be f composite with xy. So this is a composition of measurable function. So by theorem 2.1.3, composition of measurable function is measurable function, and because of the range is real numbers, so this is a random variable. So this, in fact, you can see all these are continuous function. Okay, you can verify it on yourself. Okay, I think we stop here today. All right, so we stop up to here. Okay, so no point to carry on until 9:30. I think it's good enough for today. So let's stop here. Okay, before that, once again, okay, what are the main things that you need to know? Okay, so actually you may the idea for random variable, you can follow this just using this to so you may forget about the definitions. Just look at here. What is meant by a random variable? So a random variable is a mapping. Okay, maybe I'll put it here. Just a summary once again. Okay, first. Okay, since we are only concerned with random variable, so I would directly go to random variable rather than begin with measurable functions. Okay, so let's say if you have a functions depend on here and up to here. Okay, x is a function from omega to r. Okay, r is we assign all outcome a number. Of course, when we talk about sample space, we always assume we are able to construct a sigma field. Okay, and when we come to R, easier, we always take the standard one, the Borel sigma field over here. Okay, so the elements here. Okay, I will use this. So for this, the elements is so-called Borel set. Okay, Borel set means an event whereby the sample space is R. Okay, so here I did elements here are event. Okay, I put it this way. So in this case, so then you forget this is a random variable. So you say x is random variable provided this is true. X less or equals to b. You don't have to consider all Borel set. What we need to do is we just need to consider a particular type of Borel set. This one, the pre-image of this belongs to here. So this is a first thing that you do definition. And other than that, then next thing, most of the functions are random variable. You can put it this way. Okay, maybe I would say if we consider under the standard scheme or a standard scheme. Okay, standard scheme means if we take discrete, if we consider a discrete sample space, we always take the power set. So if we have some interval of R, we always take the Borel sigma field, or we won't consider those funny kind of the sigma field, okay, under the standard scheme. So I would say most of the functions are random variable. For practical usage, you may assume that, okay, although not all functions are random variable, however, in future, you may always assume all the functions that under your I sign will be a random variable, okay? Unless I want here, but I want you to how to say that to understand the formulation theory. So I will ask you to do the verification for some of these things. Okay, but in future you may always assume the function, every function must be random variable. Okay, don't ask me to construct a what do you call it, non-random variable under the standard scheme. So that will be a very hard one. Okay, that will spend another 2 hours lecture for that. Okay, right. So just remember this. Okay, so this is the most important idea for this chapter. Before we proceed to another topic, so-called distribution functions. All right. Okay. So, any other questions? We have 10 minutes left. Any? No. Okay. Okay. So I think we stopped earlier today. All right. So we stop here and then we carry on our discussion next week. Okay. See you guys next week.